This work introduces aerial visual grounding AerialVG, a new task for intelligent drones. We provide the first dataset for this task, consisting of 50,000 annotations and 103,000 objects. Additionally, an AerialVG model is proposed to explore the positional relations among objects and achieve superior context-aware visual grounding in drone applications. In this paper, we developed the AerialVG dataset. This dataset contains 5,000 high-definition images taken from UAVs. We annotated them to ensure that they are suitable for aerial visual grounding task. In addition, we provide a specially designed natural language description for each object, which details the objects in the image and their relative positions. The AerialVG dataset provides a solid foundation for fine-grained object grounding in complex scenes from a high-altitude perspective, and especially lays a new research direction for the efficient grounding and understanding tasks of intelligent UAVs, of surrounding auxiliary objects to assist reasoning. To this end, we accurately annotated the data to ensure that the spatial relationship between objects can be fully captured, thereby improving the accuracy of AerialVG. Figure A shows the resolution distribution and word cloud for the AerialVG dataset. Unlike the Ref Coco series, where over 70% of images have a resolution around 600 x 650, the AerialVG dataset consists mostly of images with resolutions greater than 1000 x 500. This higher resolution and wider field of view make the AerialVG task more challenging. The word cloud analysis highlights frequent mentions of vehicle types, colors, and spatial positions. These annotations emphasize the importance of understanding not only object identification but also their relative locations in the environment. This rich annotation style is critical for tasks like UAV navigation, emergency response, and large-scale monitoring, where spatial relationships are essential for accurate decision-making. Figure B compares the AerialVG dataset with existing visual grounding datasets across three key aspects, i.e., the average number of words in the text, the average number of objects located in the image, and the proportion of irrelevant regions. In all three aspects, the AerialVG dataset demonstrates a higher level of challenge, highlighting its complexity and suitability for more advanced visual grounding tasks. As shown in figure, we take Grounding Dino as the baseline and design an end-to-end model for AerialVG. Grounding Dino is built on a transformer architecture, where the encoder stacks self-attention and cross-attention layers to fuse image and text features. After fusing these multimodal features, it selects the most relevant features as queries, which are highly similar to the text. These queries are then decoded in the decoder, and the final bounding boxes and logits are generated by the B-box head and class head, respectively. Unlike Grounding Dino, after embedding the image into hierarchical features using SWIN transformer, we fuse these features with text features encoded by BERT via hierarchical cross-attention, enabling the model to focus more on potential regions where objects are likely to appear. After the decoder, we introduce the relation-aware grounding module to capture the positional relationships between different objects. Table 1 presents the evaluation results of different models on the AerialVG dataset. In the zero-shot setting, existing VG models exhibit limited performance, with both Top 1 accuracy and TOP5 accuracy hovering around 10%. This result highlights the challenges posed by high-resolution aerial imagery and the unique characteristics of the aerial viewpoint, which are not well represented in existing datasets. The poor performance of these models further underscores the necessity of AerialVG as a benchmark for evaluating visual grounding in aerial scenes. After fine-tuning, TOP5 accuracy shows a significant improvement, indicating that models can better recognize and retrieve relevant object candidates when adapted to the AerialVG. However, Top 1 accuracy remains relatively low, suggesting that while models are able to identify visually similar objects within the scene, they struggle to distinguish the correct target based on spatial relationships and contextual cues. In addition to the AerialVG dataset, We also evaluate our AerialVG model on the other datasets to assess its performance on standard visual grounding benchmarks. As shown in Table 2, our AerialVG model also presents good performance across multiple metrics on the REF-COCO series datasets, achieving comparable results with previous state-of-the-art approaches. To better validate the generalization ability of our model, we conducted real-world experiments by capturing a set of aerial images using the DJI-M30T drone. The images were taken at an altitude of 50 meters with a resolution of 4000 × 3000. The images are filled with various types of vehicles, posing a significant challenge to object localization. However, as shown in figure, our model still successfully locates the objects accurately based on spatial relationship information, demonstrating its strong generalization capability. We will show more visualization results in the supplementary material.